All right, so thanks. So I want to talk about, today I'm going to talk about some modular optimization under noise, and this is a joint work with Avinatan Hassidim, who's at Bar-Ilan University and Google. What's nice, it's nice to talk about this here because this is actually the first published paper that we have from this ongoing collaboration for 3 years, okay? So what is it that we've been doing all this time? So what we're trying to do is we're trying to understand data-driven optimization, and to sort of understand that, then we want to make this distinction between that and traditional optimization, right? So in traditional optimization, which is what some of us learned in maybe middle school and maybe others in grad school, we have a certain model that we know, and that's the ground truth. We take this model, and then maybe it's a graph, and we try to optimize some sort of objective function on this ground truth, and we end up making a decision based on that. But in reality, for a lot of the problems that we started looking at, what we saw is that this is not really the story that's going on here. Really what's going on is there's some data that's generating in some sort of like a generative process. Then what happens is we actually use machine learning to learn this model. And from this model that we learn from data, then we're actually trying to make a decision by optimization. Okay? So the crux here is that there is some true function that generates the data. Using machine learning, we actually make this, we don't have the true function, we have a surrogate function. And then we try to optimize the surrogate function to come up with a decision when we evaluate it against the true function. So the question that we're asking is, when can we optimize a function f given its erroneous version f tilde? Okay? So we can ask this for any kind of function, but the interesting classes of functions that for which this question is actually meaningful is the class of some modular functions. Okay? And you'll see why in maybe a few minutes. So like we just heard from this talk, so some modularity is these are discrete functions that have this diminishing returns property. And they're heavily used in machine learning because we have objectives like mutual information, clustering, information, influence maximization in networks, and all these sort of objective functions that are kind of like naturally appear in machine learning. In mechanism design and game theory, you'll see a lot of some modular functions because this diminishing returns property models the way that agents value goods. Okay? So some modular functions are very good from a modeling perspective, but another reason why they're very good, which is the talk we just heard, is that some modularity essentially is a certificate for desirable approximation guarantees. Okay, and what I mean by that is that we can run very simple algorithms and get desirable approximation guarantees. So one example is this greedy algorithm, where we start with the empty set. As long as we haven't selected k elements, we just add the element that adds the largest marginal contribution. And we know that this simple greedy algorithm is actually gives us a 1 minus 1 over approximation, roughly 63%. And this is optimal unless either p equals np, or if you're thinking about functions that have exponential representation, you're using polynomial communication. Okay? But from our perspective, the problem is that in many cases, we don't actually know the function that we're trying to optimize. Right? And in a lot of applications like PMAC learning, sketching, and game theory, this is actually the case. Okay? So in order to understand that, what we need to understand is how do we think about some modularity under noise? So a very simple model that we can use to think about some modular functions under error or noise is the following. We're going to say that a function f has a erroneous oracle f tilde. Okay, if this f tilde is a 1 plus 1 minus epsilon approximation of f for every set. Okay? And now the question is, when we have this good approximation for some sort of small epsilon, can we get desirable approximation guarantees? So it turns out that the answer is no. Okay? So you can show that for any fixed, any constant epsilon, you can actually also show this for subconstant epsilons. Okay? If you have an epsilon approximate oracle, you would need exponentially many queries to optimize your submodular function under a cardinality constraint. Okay? And these classes of functions are actually very simple. They include coverage functions. They include actually even simpler functions. Okay? And these are actually functions that we use a lot in practice. I should just mention that this also happens for convex functions. So for all of you that don't like submodularity, you shouldn't gloat. Okay? But the implication is that just optimization with error is just inherently hard. Right? So we still have, I think, 3 or 4 minutes left, so let me just say a few more things. So the definition, an equivalent definition of error is I can say that this erroneous oracle is psi of s times f of s, where psi of s lives between 1 minus epsilon and 1 plus epsilon. So that's the definition of error. What I can do is I can modify this definition and now have a definition for noise, where I'm going to say that f has a noisy oracle if this oracle is psi of s times f of s, but now this psi of s does not live in 1 minus epsilon, 1 plus epsilon. It can live anywhere, but it's drawn from a distribution. Okay, in both models, the noise is consistent, meaning that if I query multiple times, I get the same answer. Okay. So we know that we can't do anything when we have error. The question is whether we can optimize functions under noise. And the main result in the paper is that, yes, for monotone submodular functions, we can actually, whenever k is sufficiently large, we can get these 1 minus epsilon, approximations that are arbitrarily close to 1 minus 1 over e using polynomial many queries. Okay? The nice thing about this is that it has a lot of other applications to approximate submodular functions, optimization with correlated noise, not just when the noise is IID, gives us guarantees for active learning, and gives us guarantees for discrete choice in economics and in ranking. Okay, so let me spend like maybe 2 minutes telling you about the rest 50 pages of the the paper. Okay, so what's the 2 minutes? So what's the general idea? The general idea is basically to take an arbitrary, not a random, but just an arbitrary set H, okay? And then whenever I evaluate a function, I'm going to evaluate the function with all its subsets. Okay, so I get some sort of smooth version. So what's the idea? Intuitively, when I do this kind of smoothing, then I kind of average the noise so that instead of this f tilde, I have a function f, capital F. Okay? I can then run a smooth, greedy version of this function. Okay, where instead of taking the element that has the largest marginal contribution, I take the element that has the largest marginal contribution according to this capital F. The problem is that I just optimize capital F and not the true function f that I try to optimize. Right? So what is this good for? Okay, so what this is good for is that this gives us some guarantees that we can actually use. So what are these guarantees? Basically, what I can show is I can show that if I selected an element A, then what that means is that this algorithm guarantees that the true value is greater than the value of another element when I evaluate it against a different function. What I can then do is I can then get a guarantee against an optimal solution of this sort of weird objective, but where this weird objective is the optimal solution when I discount for this set H that I selected. So this would work if H had small value. So what we do is we actually generate a bunch of these H's and run this kind of smooth greedy algorithm on every one of these small H's, and then we can get this 1 minus 1 over e approximation guarantee. Okay. So there are other sort of selling points that I want to throw at you, but you can just come to the poster. So just to conclude, I'll just say that in general, small errors can make submodular maximization and also, by the way, convex optimization hard. The good story is that for non-adversarial noise, we can get the optimal 1 minus 1 over e. So all these positive results that we have in the generalizations sort of suggest that this is kind of like the right model to think about approximate submodularity. And more generally, the moral question, I think, is what are the sort of limitations of the optimization models that we're currently using? Okay? So with that, I'll just say thanks.
Questions, yeah.
Well, if you don't have for non-monotone, if it's not under cardinality constraint, then you can just sample. You can, without looking at the function at all, you can just sample, and then you get a half approximation, or if it's half approximation, if it's symmetric, and like a third approximation. But for cardinality constraint, we don't have any, and all the techniques that I just said are going to fail when you have non-monotone functions.
Let's thank Yaron again.